Hello guys, Sir DV here again to discuss to you the probability-based load and resistance factors. So this is only a short explanation how uh, statistically your margin of safety or factor of safety is measured uh, and created, no? Derived using probability-based procedures. So particularly these are used for load and resistance factor design wherein uh, the strength, the under strength, and the overload factors, the multiple overload factors are checked in terms of reliability uh, index procedures. So to give you some basic statistical concepts, uh, we consider a histogram bar graph representing the frequency distribution of a random variable x. So this variable uh, is any argument that is used, no, to define the overload factors, and uh, those samples that were used will be collected, and a frequency histogram is prepared, uh, which is basically what this figure uh, here is showing you. Okay, for samples, the value of your argument or your variable, the random variable, is plotted and measured in terms of its frequency. So how many times such variable in as far as this value is concerned was actually observed. So a histogram bar graph or simply a frequency graph can actually be uh, plotted in this manner. If the ordinate is a percentage of the values rather than the actual number of values, then the sum of the ordinates will of course be 100%. Okay, if you are using here a unit bar graph, the sum will be 1. And the graph may be called a relative frequency distribution graph in this case. So also the probability that x will fall in between a range a and b is simply equal to the sum of the ordinates of the bar between a and b. So that's how simple the probability is measured. And of course we have to recall the basic statistical formula we need in order for us to make some computations. So we recall the definition for mean, the variance, the standard deviation, and the coefficient of variation. So these are the basic statistical tools we need to account for when we talk of such procedure. So for the mean, this is simply an average, no, of all the summation of the samples, okay, from 1 to n divided by n. And for the variance, we simply get the difference between each and every value of the variable involved, okay, from the average or the mean, and then square it, take the summation of that from I equals 1 to n and divide it by n. That's what you call the variance. And for the standard deviation, simply take the square root of the variance, we can get the standard deviation. And for the coefficient of variation, we simply divide the standard deviation uh, by the number of samples, and we get the coefficient of variation. Okay, for the probability density function, we consider now two random variables R and Q. Okay, so here X can be the resistance, and also X can be the load Q. Okay, so separately we can make use of these two random variables, and we can see that in the figure the probability of R being less than or equal to Q may be represented by the area of the shaded part under the left tail of the R curve, and this value of probability means that the failure and vice versa occurs. Okay, hence if we look into the figure that I was referring to, so these are now the individual or the separate graph of the frequency distribution in terms of a bell graph rather than a histogram, a bar histogram. Okay, so we take note that the intersection of this bell curve here for Q, the random variable Q, and the random variable R is actually located in this area. Okay, and the shaded portion under, okay, the intersection of these two curves. Okay, so this is the shaded area where uh, your R is actually less than Q, the load. Okay, so up to this point, so let's try to figure out. So at this point of intersection and beyond, okay, so we take note that the height of your Q here and height of R is equal. And at this point going to the left, okay, the height of Q is now greater. Okay, so if we look into the height of Q here is now greater than the height of R. Therefore, the load is greater than R. So what does this shaded portion signifies? So it signifies what you call, okay, so a failure area. So what does it mean that in this particular location, there may be failure that will happen, the probable failure that might happen in terms of the expectation of whatever resistance and whatever Q load is absorbed by the structure. And so how do we get away from such trouble? So we now introduce a factor of safety, and the amount of the value of the factor of safety will actually be dependent on the reliability of this undertaking. Okay, so the index, the reliability index beta, which is determined or given to us by some code giving bodies, okay, like those which involves factors of safety on earthquake, wind, etc. Okay, so the margin of safety and the reliability index are now related in such a manner that when we apply a certain index beta or the reliability index beta, the factor or the margin of safety may now be computed, no? So this margin of safety, which is computed on this basis, this procedure, is actually uh, a probability-based assessment. And the probability density function may be integrated by simply dividing R and Q. So we know that R is a